Welcome to the Walton Pi. The following is a test review that was held for a Proof Fundamentals course that covers cardinalities, injections, surjections, and the well-definedness of different functions and relations. So I guess we can just go through a bunch of different things and let me know if there's any topics that you want to go over more of or not. Okay, so let's get started by just talking about, let's just find some, alright, so let's just talk about well-defined functions. We'll start off with that. Alright, so let's try and figure out which of the following, here, one sec. There we go. Okay, so let's talk about well-defined relations. Let's just try and figure out which of the following relations are going to actually be well-defined. So let's say that we have a function from the real numbers to the real numbers where f of x is equal to x squared. Is that going to be a well-defined function? So if we're trying to figure out if it is going to be well-defined, what we have to do is we have to check if a equals b, does f of a equal f of b? If that's the case, then it is going to be well-defined. So if we say f of a equals a squared and f of b is equal to b squared, well, if a equals b, then a squared is equal to b squared. So yes, this is going to be well-defined. So this is going to be an example of a well-defined relation. Let's do another one though, where we are doing g is defined from z4 to z3, where g of the class of A in mod 4 is equal to just the class of A in mod 3. This one is not going to be well defined because, for example, class of 0 in mod 4 is the same thing as the class of 4 in z mod 4, but the class of 0 is not equal to the class of 4 in mod 3, because the class of 4 is equal to the class of 1 mod 3, which is not the same as the class of 0 mod 3. And so this is an example of something that is not well defined. So that is how we would go about doing well-definedness, showing a function or a relation is or is not well-defined. Something that does come up sometimes is a lot of times people get confused between a function being well-defined and a function being injective, because they are very similar. So injective, we start by assuming f of a equals f of b, and then we show that a is equal to b, whereas well-defined is the converse of an injective function. So that would be an example of something that we might come across if we're trying to do well-defined or not well-defined, injective, not injective. It's important to be able to tell the difference between those. Do you have any questions with well-defined relations or things like that?
No, that makes sense. Thank you.
Okay. Let's see, what else is there? Alright, let's do some cardinality things. So let's see. For example, some things that you might be asked to show might be to show that the set 0, 1 has the same cardinality as the set from 0 to 1 like this. That is something that you might be asked to show. So we'd have to show that both of these are of the same cardinality. So the way we would need to do this is we need to find a bijection f going from one set to the other. So let's have it go from 0 to 1 to 0 to 1. So we have to deal with where does 0 go. The way that I would probably approach this is to look at a graph of where elements can go to. So we're allowing 0 to be in our domain, so we are going all the way from here all the way out to 1, and then we are trying to go all the way from 0 to 1 here. So what we would probably want to do is just have a really simple relationship where it's just going to go endpoint to endpoint and map everything 1 to 1. The problem with that is we have to deal with where is 0 going to go. We can't send 0 to 0 because 0 is not in our codomain. So we can't just send 0 to itself. That would cause a problem. But then if we send 0 to anything else, that's also going to cause a problem because it's going to just go to something that is already hit. So it would not be injective. Because it's currently surjective, it's just not injective. So this is where we're going to have the idea of like non-repeating sequences. So for example, we have 1/2, 1/3, 1/4, 1/5. This is a sequence that's going to always stay inside our codomain 0 to 1, and it never repeats. This is one example. Another one might be like 1/2, 1/4, 1/8, 1/16, and so on, where we just divide each term by 2. We just need one sequence that never repeats and stays inside our codomain forever. I am going to use this second one just because it's a little bit easier to write in our function when we are defining the bijection. So what we are going to do is we have to deal with where do we send 0. So let's send 0 to 1/2. So we are going to just send 0 right there to 1/2. The problem now is 1/2 now is mapped to by 2 different elements. So we are going to send that second one, we are going to remove it and send that to the next term in the sequence. So 1/2 is now going to go to 1/4. But now 1/4 goes to more than one thing, so we are going to send what 1/4 originally was to half of it. And we are going to just keep repeating this process. Whoops, I have them backwards. We're going to just keep repeating this process so that we can be able to have a way of continuing to write this function. So the way that we would describe this is going to be as a piecewise function. So we are going to say f of x is equal to, and then define a piecewise function. It's equal to 1/2 if x is 0. It's going to be equal to half of x if x can be written as 1 over 2 to the n, where n is a natural number, and then x otherwise. So this is basically saying we have this sequence 1/2, 1/4, 1/8, 1/16, and so on, where if it's in that sequence, send it to the next term in the sequence, and then what goes to the first term? That is 0, the point that we had to deal with to start. And so this is going to be our bijection that we would use in the proof. Does that make sense why we would choose that?
Kind of.
Okay, what part is confusing for you?
I don't really know which part I got lost at, but I mean, it kind of, I don't know. I don't know how if like I had to do it, I don't think I would be able to.
Okay, let's do another example, and we can work together to figure out what the sequence would be that we would need to follow. So let's instead try and show that the interval 0 to 1, both ends closed, is the same size as the interval 0 to 1 like this. Whoops. Actually,
Can you explain why you like did the x, one on the x-axis and one on the y-axis?
yeah, so that was just a way for me to visualize what things need to go where. So, because often we say like f of x equals y, so we'd have like, here's our x-axis, here's our y-axis, and we have some function like this. We are saying that our x's are our inputs and our y's would be our outputs. So this would be a function defined from the real numbers to the real numbers. So here we need a bijection f that's going to go from closed interval 0 to 1 to the open interval 0 to 1. So the way that I would graph this to try and get a visualization for what I would need to do would be I would have my inputs 0 to 1 and then my outputs 0 to 1. Does that make sense?
Yeah, and then can you explain like what a bijection is?
Yeah. So a bijection, this is a function that is injective and surjective. Those are the only two conditions for it to be a bijection. So for it to be injective, what that means is we would have to say that if f of a equals f of b, then a equals b. So in other words, this is 1 to 1. And then surjective is for any output, there exists an input such that f of that input is equal to that output. Or in other words, surjective is onto. Did that answer your question with bijectiveness?
Yeah.
Yeah. So we just need to have f be a bijection. So the way that I do these is I like to just try and figure out what is going to be a good starting function, and then if I need to modify it to get it to work out. So for example, in this case, a good starting function, since it's 0 to 1 to 0 to 1, we probably just want to stick with the line that goes endpoint to endpoint. So this is our starting function that is almost a bijection, but it's not quite. So it can't be included on the endpoints because we can't map to 0 or 1. So that's why we can't include the endpoints. But that means that we still have to send this 0 and this 1 to something.
Yeah.
And so this is where we're going to be coming up with some different sequences to figure out where to send different things. So we just need any sequence that stays inside the interval 0 to 1. So what's your favorite sequence that's always bigger than 0 and less than 1?
I like the one you used, like 1 over 2, 1 over 4.
Yeah. Yeah, so this is a sequence that works out a lot of the time. And so what we have to do is we have to say, well, we have to deal with 0 and we have to deal with 1. Those have to go to something. So the way that we can deal with it is we can say, well, 0 is a number we have to send somewhere. So let's send 0 to 1/2. So if we were to look on the graph, that would then be sending 0 to 1/2 right there. The next number we have to deal with is we also have to deal with 1. We have to send 1 somewhere. So let's send 1 to 1/4. That's just the next term in the sequence, so we are just going to send 1 to 1/4. Does that make sense so far?
Yeah.
Okay. The problem now is this function is no longer no longer injective. Because those two values, there is now a second, there are now two inputs that give the same output. Specifically, 1/2 also sends to 1/2, and 1/4 also sends to 1/4. So what we have to do is we have to say, well, we can't send 1/2 to itself anymore, so let's now send 1/2 to the next term in the sequence that is not already sent to. So we are now going to say 1/2 no longer goes to itself, but now 1/2 goes to 1/8. Does that follow so far?
Yeah. So it can't have more than one of the same x, b, y.
We can't have two different inputs give the same output. Yeah.
Yeah, that makes sense.
And so what we're going to have to do is 1/4 is now sending to two different things. So we're going to take 1/4 and send it to the next term. So 1/4 is going to now be open there and go to 1/16. 1/8 now has two things, so that goes to the next term. So that'll go to 1/32. And we're just going to continue this process forever. But because the sequence always stays inside 0 to 1, it's going to work out perfectly fine. Because the sequence never leaves the interval, there's always another term we can move something to. So we can always just keep pushing the problem further down the line, and because there isn't an end to the line, that ends up solving our problem, because we can just push it on forever, so we've eliminated the problem.
And then that will always stay inside the codomain, so it always works out.
Yeah, and so that's how we can get our function, and so that means we can say that our function, f of x, is going to be a piecewise function. So we have a few different situations. We have the situation if x was 0. We had the situation if x was 1. We had the situation if x is equal to 1 over 2 to the n, where n was a natural number. And then those were the three special situations, and then we just had our otherwise case. So most of the time it's going to just be itself. So most of the time it just goes to x. But in these special circumstances, we have to say where does it go to. So if x is 0, it goes to 1/2. If x is 1, it goes to 1/4. And if x is in this sequence, so in other words, if it can be written as 1 over 2 to the n, we are just going to send it two terms farther down the sequence, or in other words, dividing that term by 4. That's what it means to be two terms further down in the sequence. Does that make sense?
Would it also be correct to write 1 over 2 to the n plus 2?
Yes, that would be a perfectly valid way of writing that one as well. So we could also write that term as 1 over 2 to the n plus 2. That would be another valid way of writing the same thing.
Okay, yeah, that makes
Yeah, so this would be our bijective function that we would use to show that these two intervals are actually the same size. So we would use that function, and then we would have to prove it's bijective. So we'd have to prove it's injective, and we'd have to prove it's surjective. But the way we constructed it is going to work out. So that would be the function we would want to use.
Okay, sounds good.
Okay. Would you like to go through the rest of that, or do you feel good with where that's at?
Going through like proving how it's injective and surjective?
Yeah.
Yeah, we could do that.
Okay. So, going back to our function, we just need to prove it's injective and surjective. So f is injective. So we're going to start by assume that f of a is equal to f of b. Now we're going to kind of go through a few different cases. And these cases are precisely these four cases that we have in our piecewise function. Those are going to be the four different cases. So, case 1, f of x, f of a equals f of b equals 1/2. We know that x equals a equals 0 is one possibility. We now need to show it is the only possibility. If b is equal to 1, then f of b is equal to 1/4, which is not 1/2. So we're good there. If b can be written as 1 over 2 to the n, with n being a natural number, then that means that b is less than or equal to 1 over 2 to the 1. But if b can be written that way, then f of b is equal to, f of b is less than or equal to 1 over 2 to the 1 plus 2, which is 1/8. So that's not going to work. And then if b cannot be written as 1 over 2 to the n, or b is not equal to 1, then f of b is equal to b, but since b can't be written as 1 over 2 to the n, this guarantees it's not equal to 1/2. So a equals b equals 0 is the only solution. And so that's what we would have to do for each of these different cases. So case 1, a equals 0 is the only solution. Case 2, we are going to do f of a equals f of b equals 1. Not 1. 1/4.
Then you would just go through the other three and do we just did, showing how that's the only thing.
Yeah, it's the only way for us to get that specific output. So case 2 is going to be pretty much the same. Case 3 is going to be the third case. And then case 4, f of x equals x, that's very easy to show is injective for those situations. So yeah.
Okay, and then how would we show that it's surjective?
So for it to be surjective, let's go right here. So to show that f is surjective, we would start by saying for any y in our codomain, 0 to 1, we now need to find the specific specific input that gives us that output. So our different cases are going to be the different outputs we could get. So we'd have case 1, y is equal to 1/2. Let x be equal to 0. F of 0 is equal to 1/2. So we have found an input that gives us y equals 1/2. Case 2, that would be y is equal to 1/4. Let x be equal to 1. F of 1 is equal to 1/4. Perfect. We found an input that gives us that output. What on earth? Where did that come from? Okay. Case 3, y can be written as 1 over 2 to the n plus 2, where n is a natural number. Let x be equal to 1 over 2 to the n. Then f of x is equal to y. So there's case 3, and then case 4, it's none of those, in which case let x be y. And then that's going to give us all of our cases. Y is none of the above. Let x equal y. Then f of x is equal to x is equal to y. And so that would be all three cases to show that our function f was a surjective function. Does that make sense for you?
Yes, it does. Thank you so much.
No problem. Do you have other topics you want to touch on or different things like that?
Would we be able to just go like through the practice test and go through those problems?
I believe so. If I have the same one, is it the one that says like sample exam 3?
I think so. It's on Canvas.
Okay. I don't have access to that, but I do have a practice test, and I'm guessing it's going to be the same one. So I can go through the one that I have, and then we can be able to see how, if it matches, great. If not, then we can try and go through the ones that you have as well.
Okay, sounds good.
Okay, so this one, we're going to start off, at least mine starts off with true-false statements. So the first one is that any infinite subset of an uncountable set is uncountable. Is this going to be true or false?
I don't know.
Okay, so let's try and think of some uncountable sets. So some uncountable sets are like the real numbers, the interval from 0 to 1, the power set of the natural numbers. These are uncountable sets. If we take, for example, the real numbers, one example of an infinite subset are the natural numbers. That is a subset of the real numbers, and both are infinite. But the natural numbers are actually countable. So that tells us that this one is false. A similar question that we might have been given that would actually be true, and this is actually a theorem in your book, is if we drop the uns in front of these, any infinite subset of a countable set is countable. In fact, you can actually drop the infinite piece, and then that's still true. Any subset of a countable set is countable, but as it's written with any infinite subset of an uncountable set, that is not guaranteed to be uncountable. So that one is actually going to be false. Let's do n cross q cross n is countably infinite. Is this going to be true or false?
I don't know. I think I missed the countable
Okay.
lecture. I think
Okay. So this is going to be true. The reason for that is that if we look at n cross n, n cross n, this is as if we were to write like a set of ordered pairs where we have like, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, where we are writing them like this, we need to be able to provide an ordering to show that this is going to be countable. So if we were to go in this direction, this is providing an ordering where there is now a specific order, and we are going to hit every single element one time exactly. So if we take two countable sets and we take their cross product, that is going to also be countably infinite. So what we can do is we can kind of say, well, n cross n, that's countable. Cross another countable set, that's still countable. Cross another countable set, well, that's still countable. So it's always going to be countable, and since it's infinite, it's going to be countably infinite. So that's why this one is going to be true. Does that make sense?
Can you explain one more time what it means to be countably infinite? Is it just like
Mhm.
being able to count like these into crosses?
Yeah, so if we can provide an order, it's going to be countable. Specifically, countably infinite, it is defined, means that there exists a bijection with the natural numbers. So that's what it means for it to be countably infinite. So the way that we went through and did this, the way that we have our bijection is 1, 1, well, that's our first thing. Our second thing is 2, 1. Our third thing is 1, 2. So there's 4, there's where 5 goes, there's where 6 goes. 7's going to be here, this one's 8, this one's 9, this one's 10. By being able to draw these arrows, this provides an order that tells us what our bijection would be defined to be. Does that make sense?
Okay. Yeah.
Okay. Let's do another one. Let's see. So 3x is a set. The set x comma x, where x is from the set x, is a function f defined from x to x. Is this going to be true or false?
This is true.
Yes, this is going to be true. Because the only requirement for a function is that everything in the domain, so everything in x, goes to something. So everything in x goes to something. Well, this goes to itself. And then we have to show it's well-defined. This is well-defined as well. And so because it's well-defined and defined for every element, it is going to be true. So yeah. Let's see. Next one. The image of f defined from R to R, where f of x is equal to sine of x, is the interval 0 to 1. Is that going to be true or false?
I think that one's true, but I'm not sure.
Okay, so this one's actually false. The reason for that is the image. Whoa. Zoom back in. Alright, so the reason for it is the image is the set of all outputs that we actually get. So the different outputs we can get from sine of x, that's going to be anything from negative 1 to 1. So the image of sine of x is going to be negative 1 to 1. If it had been the image of sine squared, then that would have been true, but because it was just sine of x, it's negative 1 to 1. Okay, let's see, the next one. So S is not the empty set. There is a surjective function f defined from the power set of S to S. Is that going to be true or false? Okay, so let's look at a couple examples. So for example, if we have S is the set 1, 2, then the power set of S, that is the set of all subsets of S. So that would be the empty set, the set containing 1, the set containing 2, and then the set containing 1 and 2. That would be the power set of S. So we could send 1 to 1, and we could send 2 to 2, and then it doesn't really matter where we send these other elements. So this is an example of a surjective function from the power set of S to S. So this one is actually going to be true. And this is going to be true no matter what, because the power set of S is always larger than the set of S, which means that there's always going to be a surjective function from the power set to S. Does that make sense?
Yeah, it does. I'm just writing down something. Okay.
Let's see, so number 6, there exists a set S such that the cardinality of the set S is greater than the cardinality of any other set.
I feel like that one would be false.
Yeah, this is going to be false. And the reason for that is the cardinality of the power set of S is always strictly greater than the cardinality of S. So the power set of S, that is a valid other set, which means that the power set of S has to be bigger than S. So this is going to be false. There is no largest set. So yeah, that one is going to be false. Let's see, the cardinality of the power set of the integers is equal to the cardinality of the real numbers. Is that going to be true or false?
That one looks false too.
So this one is actually true. The reason for that is, so the cardinality of the natural numbers is equal to the cardinality of the integers. And this tells us that the cardinality of the power set of the natural numbers is equal to the cardinality of the power set of the integers. However, the power set of the natural numbers, that is defined, or there's a theorem in your book that says that that is the same cardinality as the real numbers. So we are able to then say that means that the real numbers have the same cardinality as the power set of the integers. So this one is going to be true. Okay, next one is if f is a function from a to b and g is a function from b to a, and g composed of f is equal to the identity on a, then f is bijective. Is that going to be true or false?
I don't know. If I had to guess, I would say that it's true, but I don't know.
Okay, so this one is going to be false. So let's just try and come up with some examples where g composed of f is the identity. So we have some set A, we have some other set B, and we are trying to have g of f be the identity. So let's say that we have the numbers 1, 2, 3, and 4 in A, and then in B we have the elements A, B, and C. Let's actually switch these around. Okay. So we have 3 elements in A and 4 elements in B. So F goes from A to B. So let's send 1 to A, 2 to B, and 3 to c. So f is going to be our red function. We then have g can send a back to 1, b back to 2, c back to 3, but then we need to send d somewhere. So let's just send d to 3 as well. So if we look at g of f, we do f first and then g. Well, follow the red arrows and then follow the green arrows back. This is equal to the identity on A. Everything just goes straight back to itself, but it is not surjective. Nothing maps to this element D. So this F would not be surjective. So we found a counterexample. So for a lot of these, just look to see if a finite set where both of them are finite is a good example that would provide a counterexample.
Can we do like an example of like G composed of F? Could we like practice how you do that?
So how would I figure out what G composed of F is?
Yeah.
Okay. Yeah, so if we were to look at, so here in this example we have F of 1 is A, F of 2 is B, F of 3 is C, and we have G of A is 1, G of B is 2, G of C is 3, and G of D is also 3. So what we would have is we'd have like G of F of maybe 2, for example. This is going to be equal to G of F of 2. Well, F of 2 is B, so this is going to be G of B. G of B is equal to 2, so we get back 2. So that would be how we would find G of F. Did that answer your question?
Yeah, and then it's equal to the identity on A.
Mm-hmm.
Only because we're doing F first. If we did F composed of G, then what would it equal?
Yeah, so if we did F composed of G, that would not be the identity. So if we did F composed of G, we would need to go through each of the different things in the set B. So we'd look at what happens if we look at A, if we look at B, if we look at C, and if we look at D. So if we look at all of these different things, this is going to be F of G of A. So F of 1, this is equal to A. F of G of B, well, that's going to be F of 2, so that's equal to B. This one is F of G of C, so that's going to be F of 3, that's equal to C. And this one is going to be F of G of D, so F of 3, so this is equal to C. And so this last one is actually why it's not equal to the, this is why F of G is not equal to the identity on B, because of this last term.
Would we ever need to know like what it is equal to?
Like you might be asked to compute what's the composition of these functions, in which case you would do something like this. But for like a generic proof where you're not given what those functions are, you probably would not need to.
Okay.
All right. So the next one. Alright, so we have f defined from the real numbers to the real numbers, where f of x is equal to x squared plus 3. Then f inverse, or the preimage of 4 and 7, is equal to 1 comma 2. Is this going to be true or false?
I don't know.
Okay, so let's look at what the graph of x squared plus 3 would be. So we got something like this. So we are looking for the preimage of 4 and 7. So we are looking for all of the inputs that give those outputs. So just looking at this, we see we should get 4 different inputs to give those outputs. So just from the fact there's only 2 listed, we know this is probably going to be false. And so it is actually, because we can go through and figure out that the preimage of the set of 4 and 7, all the inputs that give us 4 and 7, so we do have 1 and we do have 2, but we also have -1 and -2. So it's going to be the set -1, -2, comma 1, comma 2. So that's actually what the preimage would be. So the preimage is the set of all inputs that give those outputs, not just some of the inputs that give the outputs.
Okay. Is there like a way to tell the difference between the inverse of f and the preimage, or do we just have to like?
So they are the same if our function is injective. This function is not injective. Therefore, this is the preimage and not the inverse.
Okay. So then does it just not have an inverse if it's not injective?
Correct. It does not have an inverse if it's not injective. It has an inverse relation, and that's what this preimage is saying the inverse relation of 4 and 7, those are all going to be -1, -2, 1, and 2. But there is not an inverse function because it's not injective.
Okay. Okay. Yeah. Sounds good.
Alright. Number 10, we got f is defined from the real numbers to the real numbers, where f of x is equal to x squared. Then f restricted to 0 to 1 is injective. Is that going to be true or false?
That's true, right?
Yeah, that is true. Because if we were to look at the graph of x squared, we have that. But if we are only looking at 0 to 1, that's just this piece here, and that is going to be injective. So yes, this one is going to be injective.
But then if we were to take it like the negatives as well, then it wouldn't be injective?
Yeah, f restricted to like -1 to 1, this is not injective. That would be correct.
Because there's more than one output.
Yeah, there's more than one input that can give the same output.
Okay, yeah.
Okay. Do all of those make sense? Are there any of those topics you'd like to go into a little bit more depth?
Could you zoom out so I can see all the questions?
Yeah. I'm going to zoom out a ton. Here, I'll show the bottom couple, and then I can go up if you want.
Yeah, you can go. I think just number 7. Like,
Okay.
I understand that it's true, like, the way you explained it is good. I just don't understand why the cardinality of the natural numbers equals the cardinality of the integers. Do you have time to explain that, or should I just look in the book?
So, I know it's in the book. So, an explanation that we could do right now with it is, so we know that the cardinality of the power set of any set is going to be greater than the cardinality of that set. So if we are looking at the cardinality of the natural numbers, we know that the cardinality of the power set of the natural numbers has to be bigger than the cardinality of the natural numbers. And this is, the cardinality of the naturals is infinite. And specifically, this is countably infinite. Which tells us that the power set of the natural numbers has to be uncountable. If it was countable, then there would be a bijection between the natural numbers in that set. But because the cardinality of the power set of the naturals is bigger than the cardinality of the natural numbers, we know there cannot be a bijection. So we know it's at least uncountable. The reason why this is then equal to the cardinality of the real numbers, that is a bit more complicated, and that is something that I would look in the book for, because that's a fairly complicated proof. That's something that you can now just accept, that I would just remember, because the proof is a bit complicated to show why it's equal to that, but it is in fact equal to it, because you have to show that there's a bijection between the real numbers and the power set of the natural numbers, and that's a bit challenging to do.
So on a test, we wouldn't have to show why they're equal, we just have to know that they are equal to each other?
Yeah, it would be unlikely that you would be asked on a test to prove the real numbers are the same size as the power set of the natural numbers. It is unlikely that that would be a test question. It might be a test question to show that, it might be a test question to show that the cardinality of the interval 0 to 3 is the same size as the cardinality of the power set of the rational numbers. But then this is something that you would do by saying, well, this side is equal to the cardinality of the real numbers, this side is equal to the cardinality of the power set of the natural numbers, and so then these you already know are true, so that's how you would approach it. But showing this is equal to that, that is unlikely to be on your test. I can't guarantee it, but it is unlikely because the function is tricky. If you want to see the function, I would go and look at the tests at the book, because it does go through it there, but it is a messy function that is not a fun one to try and come up with.
Okay.
Alright. Do you have any other topics you want to go over, or shall I just continue on into the multiple choice section?
You can just keep going.
Okay. Alright, so let's see. We have A is the set 1, 2, 3, 4. B is the set 2, 5, 9, 14, and 20. We have R is a relation from A to B, where R is equal to the set of ordered pairs 1, 9, 2, 2, 3, 20, 4, 5. So the question is, which are functions? Whoa, let's make that smaller. So the question is, which of R and R inverse are functions? So let's start off and figure out, is R a function? So is this a function? So does this...
I think it is a function.
Yeah, so R is a function. Yeah, because every input gives exactly one output. 1 goes to 9, 2 goes to 2, 3 goes to 20, 4 goes to 5. And nothing goes to more than one thing. So R is a function. How about R inverse? Is that a function?
sorry, can you say that one more time? I had a thing call really quick.
Yeah, how about R inverse? Is that going to be a function?
Is R inverse, do you just like switch the order of the numbers?
Yeah.
So that would also be a function?
So R inverse is going to be like 9, 1, 2, 2, 23, and 5, 4. But this is not a function. The reason it's not a function is 14. 14 does not go to anything.
Oh, yeah.
So this is not a function.
So R inverse is from B to A, right?
Yeah, R inverse is from B to A, and it is not a function, because not everything in B goes to something in A.
Okay. Yeah, that makes sense.
Let's see. The next one is asking which are bijective. So I'm just going to write down a bunch of functions, and you try and figure out which of these are bijective. So we have f from R to R, where f of x is equal to x squared. G from n to n, where g of x, or I guess g of n is n plus 1. H from R to R, where h of x is equal to 2x plus 1, and j defined from the naturals to the naturals, where j of n is 2n plus 1. Which of these are going to be bijective?
So the first one is not bijective. Right?
Yep, correct. This one is not injective and not surjective. So yep, that one is definitely not bijective.
And then I don't know which of the other three. I would say H, and maybe not as well.
Okay. So if we were to go so let's look to see where different things go to in these different functions. So like g of 1 is 2. The next natural is g of 2. Well, that's going to give us 3. G of 3, well, that gives us 4. So g is injective, but it is not surjective. The reason why? Well, we can't get 1 as an output. So G is not surjective, so it is not going to be a bijection. If we look at H, well, any input is just a real number, and we are getting out 2x plus 1. So if we were to look at a graph of H, it's just going to be this line. So this one is actually a bijection. So H is going to be bijective. You could go through and prove it if you wanted. How about J? Is J going to be injective, surjective, or bijective?
So that one's not going to be bijective because it's not surjective.
Yeah.
That was the second one.
Yeah, this one is not surjective. Because
It is injective though.
it is injective, but it's not surjective. We can't get the output of 2, for example. So our answer is only H. H is the only bijective function.
Okay, yeah, that makes sense.
Okay. Let's see. We got X is the set of 1, 2, and 3, which are functions from X to the real numbers. Oh, whoops, not X to the real numbers, X to the integers. We got 1, 1, 2, 3, 3, 5. F of n equals n squared for all n in X. 1, 1, 2, 1, 3, 1. And then 1, 1, 1, 2, 1, 3. Which of these are functions?
I would say that the first two are functions.
Yep, so those two are both functions.
The other two are not.
Okay, so the third one is actually a function. The reason for that is each input gives exactly one output. It doesn't matter that all the outputs are the same. That only impacts if it's injective or surjective. So this one is not injective,
But it's still a function.
but still a function.
And then the fourth one is not a function. Is that just because 2 and 3 don't have any outputs at all?
Yeah, so this one's not a function for two reasons. The first reason is that 2 and 3 have no output. So that's one reason it's not a function. The other reason it's not a function is 1 has multiple outputs. So this one is not a function for two different reasons. Yeah. So the first three would be functions, the last one is not.
Okay, yeah, that makes sense.
Alright, let's see. Let's see, we need to figure out which are well-defined. So we talked about one of these earlier, but the others we did not. So we have f from the reals to the reals, where f of x is equal to x cubed minus x. G defined from z4 to z3, where g of x bar is equal to class of x, where this is z4 and this is equivalence in z3. We have h defined from the rationals minus 0 to the real numbers, where h of the rational number is just 1 over itself. The set 1, 1, 2, 1, 3, 1. From the set 1, 2, 3 to the naturals. So which of these are going to be well defined?
The second one is not. That's the one we did earlier, right?
Yep, this one is not well defined because g of class of 4 is not the same as g of class of 0. But class of 4 and class of 0 were the same, so yes, that one is not well defined. How about the other three?
I feel like the first one is well-defined.
Mm-hmm. Yeah, if we put in the same real number, we're getting the same output. That one's going to be a well-defined function.
The third one, I think, is as well.
Yep, the third one is also well-defined.
And then the fourth one, I don't think is well-defined.
Okay, so are any of these inputs the same?
No.
No, so none of the inputs are the same, but that's how our function is defined. So for it to not be well-defined, we have to have the same input and different outputs. So this is going to be well-defined. If we were to go up here though, this would not be well-defined because we have the same input but different outputs.
Okay, so for a function to be well-defined, it just has to be like in the output set. It doesn't have to have each one.
Yes, it just has to go somewhere to the output set. It doesn't matter if they're all going to the same thing. That's perfectly valid. All that matters is the same input does not give different outputs. So here, class of 4 and the class of 0, those are the same input in Z4. Because they're the same input, if it was well-defined, they would have to give the same output. But because they give different outputs, that is why they are not well-defined. The same input gives multiple outputs. That means it's not well-defined.
Okay.
Does that make sense?
Yeah, that makes sense.
Okay. Which have the same cardinality? So we have the power set of the natural numbers, we have the interval 0 to 1, we have the power set of the real numbers, and we have the real numbers cross the real numbers. So which of these have the same cardinality? Are there any of these that you see or know have the same cardinality?
Would A and D have the same cardinality? Are the real numbers by the real numbers like the same cardinality as just the real numbers?
Yeah, the real numbers cross the real numbers does have the same cardinality as the real numbers. So that means that these two at least have the same cardinalities. Does B or C, do either of them also have the cardinality of the real numbers?
I think B does.
Uh-huh. Yeah, so B also has the same cardinality. So that one also does.
And then C doesn't because the cardinality would have to be bigger.
Yeah, the cardinality of this has to be bigger than the cardinality of the real numbers. So that means that A, B, and C, or A, B, and D all have the same cardinality, but the C option does not. So that one does not have the same cardinality. Yeah. Okay.
Okay, yeah, that would make sense.
Awesome. Okay. Let's see. So, alright. I'm not doing this one exactly. That one's too big of a thing. So if S is equal to the set 1, 2, 3, 4, and we have F going from S to the power set of S by F of whoops, by f is equal to the set of ordered pairs 1 comma the set 2 3, 2 comma the set 1 3 4, 3 comma s, and 4 comma the set containing 1 2 and 4. What is the Barber set?
Can you explain to me what a Barber set is?
Yeah. So the Barber set of a function f. This is the set of elements in our set S such that x is not in f of x. So, for example, we would go back through and look at each of these elements, 1, 2, 3, and 4, and see which of those are in their in the image of are in their own image. So, for example, if we look at f of 1 is equal to the set containing 2 and 3. Is 1 in the set containing 2 and 3?
No.
No. So because it's not in its image, that means that 1 is in the Barber set. Okay? So then we look at 2. Is 2 in its image?
No, so that would also be part of the Barber set?
Yep, so that would also be in the Barber set. How about...
And then 3 and 4 are both in their image, so they're not part of the Barber
Yeah,
set.
3 and 4 are both in their image, so they are not part of the Barber set. So this is what the Barber set would be.
Okay, that makes sense.
The reason that we like the Barber set, or the reason that you cover the Barber set, is because the Barber set is used in proving that there is not a bijection. So the Barber set of a function is used to show that there does not exist a bijection from a set S to its power set. So you can use the Barber set to prove that.
Okay, that makes sense.
So that's why we use it. That's why it gets mentioned. If you want to see like more stuff about the Barber set, I made a YouTube video about the Barber set. So you can find that at like the Walton Pie on YouTube. So I explained the Barber set more there if you want to be able to see more about that. But yeah, this is what the so that's what the Barber set is. That's what it gets used for. So the Barber set of a set does not exist. You have to also have a function. So the Barber set with respect to what function? Because we need a function to define the Barber set. So because we have this set and this function, we have a way to find the Barber set.
Okay, sounds good.
Alright, so let's see. Next one. S is countably infinite. Let's see. Cardinality of T is bigger than the cardinality of S. Is T, the options are finite, countable, countably infinite, uncountable, or has cardinality of the real numbers, also called continuum cardinality. So which of these is true?
A or B.
Yeah, so it's not finite or countable.
I don't think it's C either.
Correct. It's not C, because if it's countably infinite, this would mean that the cardinality of T is equal to the cardinality of the natural numbers. But since S is countably infinite, we know that that is also equal to the cardinality of the natural numbers. So it can't be countably infinite if it's bigger than a countably infinite set.
Yeah, I probably would guess E.
You would guess E?
Yeah, I don't really know what continuum cardinality is.
So continuum cardinality just means it has the same cardinality as the real numbers. So if all we know is that T is bigger than the natural numbers, does that guarantee it has the same cardinality as the real numbers?
No.
No. So it's not guaranteed that it has continuum cardinality. All we know is that it's uncountable. Like maybe T is the power set of the real numbers, or maybe it's the power set of the power set of the real numbers. All we know is it's uncountable. We don't know what size cardinality it has, only that it's uncountable.
Is the set of natural numbers like the largest thing we can count?
Yes.
So anything larger than that is uncountable?
Yes, anything that you can show has a larger cardinality than the natural numbers is uncountable. Some sets that are countable though, so countably infinite sets. Like for example, we have the natural numbers, we have the integers. Now the natural numbers are a subset of the integers, but the integers and the natural numbers have the same cardinality. That's something that can get a bit confusing sometimes, but that's something that's going to be true. So just because it's a subset does not mean that the set that is containing the first set, so just because like A is a subset of B, this does not imply that cardinality of B is bigger than the cardinality of A. Because when you're dealing with infinite sets, that is not going to always be true.
Yeah, that makes sense.
Yeah, so like other things like natural numbers cross the natural numbers, the rational numbers cross the rational numbers, cross the rational numbers, cross the rational numbers, those are all countable sets. But the real numbers are not an example of a countably infinite set. Those are uncountable.
Okay. So the integers are also countable then?
Yep, the integers are also countable because we can list them in an order. For example, we could list the integers as 0, 1, -1, 2, -2, 3, -3, and so on. So because we can list them in a specific order, that means that they are countable. However, we can't list the real numbers, and that's actually the proof that they are uncountable, that you can't count them.
Okay, yeah, that makes sense.
Okay. Any questions with this?
No, that makes no sense. Thank you.
You're welcome. Okay. Let's see, the next one. We have F is defined from Z mod 4 to Z mod 4 by, let's see, where we have F of the class of A is equal to the class of A cubed. Is F injective, surjective, or bijective? So let's figure out if F is any of these.
I'm not sure.
Okay, so for this one, just go through and figure out what are the different possible inputs. So we could have f of class of 0, that's equal to class of 0 cubed, that's equal to the class of 0. We could look at f of the class of 1, that's class of 1 cubed, that's the class of 1 cubed like that, so that's the class of 1. F of the class of 2, that's the class of 2 cubed, so that's the class of 2 cubed, so class of 8 equals the class of 0. F of the class of 3, see, class of 3 cubed, class of 27, 27 mod 4 is 3. Okay, so now that we have this, does this help us figure out if it's injective, surjective, or bijective? Or possibly,
Yeah.
okay. So, what does it tell us?
Okay, so for something to be injective,
Uh-huh.
it has to have like an AY for every x in the function. That is, they can have more than one of the same y for each x. So it would be injective, right?
So that is well-defined. What you just described is well-defined. So well-defined is where for any one input, there exists only one output. So what you just described was well-definedness. Injective is if f of a equals f of b, then a equals b. So for injective, that means that for any output, there was only one input that gave us that output. So here we have the same output from two different inputs. So because we had the same output from two different inputs, this is not injective.
Okay.
Does that make sense?
Yeah, that makes sense. I just need to practice like what an injective function is. Go over that.
Okay. Is this one going to be surjective?
That one is surjective, right? Because for every output, there's at least one input.
So for surjective, that says that for everything in our codomain, there is an input that gets us there. So our codomain is the class of 0, class of 1, class of 2, and class of 3. There's nothing that goes to the class of 2. We have something that goes to the class of 0, we have something that goes to the class of 1, we have something that goes to the class of 3, but we don't have something that goes to the class of 2.
If we kept going, could we find one, or
Well,
will there never be
it
one?
turns out that this function is well-defined, which means if we continue to go down, so like we look at f of the class of 4, this is going to also be the class of 0, f of the class of 5, that's the same as the f of the class of 1. This is also going to give us the class of 1. And then f of the class of 6, well, that's going to give us the class of 0 again. So even if we kept going, we would continue to never manage to get 2. So it is not surjective because we can't get the class of 2 out from our function. So it is not surjective.
Okay, then there would be D. None of the above.
Yeah, because if it's not injective or if it's not surjective, it's not bijective, so the answer is none of them. It is just a function. It's not injective, not surjective, it's just a function.
It is well defined though. Here.
It is well defined. We didn't go
Okay.
through and prove it was well defined, but it is going to be well defined.
Okay.
So if you wanted to try and prove it was well defined, you would be able to do that. Okay, we have F from A to B, and we have G from B to C. They're both functions. We are then asked which are always true. We have if F is injective and G is surjective, then G of F is surjective. We have B. I need a bit more space for this one. If F is surjective and G is injective, then G composed with F is injective. C, if F is bijective and G is surjective, then G of F is surjective, and D, if F is bijective and G surjective, then G of F is injective. So one of these is always true, the others can be false. Okay, so the way that I approach these is I look to see if I can find very extreme examples that then provide a counterexample to the conclusion. So for example, if we were to start at the very first one, F is injective. We need a very extreme injective function. So let's say that A is the set containing 1. And so then F of 1 is equal to 2, where we can then say that B is equal to the set of maybe 2 and 3. And then if G is surjective, then we need to say, well, that means that G of 2 equals something. So let's say is equal to 4, G of 3 is equal to 5. So that would tell us that C is going to be the set of 4 and 5. So I just constructed an injective function F and a surjective function G. We are then told G is G of F surjective. Well, let's look to see what would G of F be. So G of F, well, that means we are doing F first. So our only input has to be 1. So that's going to be G of F of 1. So that tells us that we got G of F of 1 was 2, G of 2 is 4, and we are only able to get that. So is this a surjective function? no, we can't get 5. So that means that g of f is not guaranteed to be surjective. So A is not always true. Does that make sense how I made this very very extreme example give us a counterexample?
Yeah.
Yeah, so then we could do the same thing for surjective and injective. So let's say that we have f of x equals 1 for all x. So that if that's our very extreme function, that means that b has to only have one element. So b is the set b equals 1. And then let's say that g of 1 is equal to 2. So that tells us that c is going to be the set 2. Is g of f injective? Well, f of x equals 1 for all x in A, but we aren't told what A is. So maybe let's say that A is the real numbers. Very, very large set. Well, g of f of x, well, that's going to just be g of f of x. So that's just going to be g of 1. That's equal to 2. So everything in the real numbers goes to 2. That is definitely not injective. So those are the sorts of ways that I would go about this and try and find very extreme counterexamples. It turns out that C is going to be true. If F is bijective and G is surjective, then G of F is going to be surjective, but then D is going to just be false. Again, you could be able to construct these sorts of very extreme examples. Does the process make sense of how you'd be able to figure that out?
Yeah, that makes sense.
Okay, let's see. Let's see, so we have f defined from a to b is a function, and we have x and y are subsets of a, and w and z are subsets of b. And then we are asked which are true. F inverse f of set x is equal to the set x. F of x intersect y is a subset of f of x intersect f of y. C f of x union y is a subset of f of x union f of y. F inverse of z intersect w is equal to f inverse of z intersect f inverse of w, and f inverse of b is a subset of A. So which of these are going to be true? So sometimes it helps if you have these different sets. So there's x, there's y inside A, and over here is going to be B with W and Z. So all we know is that f is a function from A to B.
I don't know which one of these would be true.
Okay. So for these, if you're just trying to figure out which are true, see which ones you can come up with counterexamples for. So let's say that f sends everything to one point. So that is a very extreme function. So all of a goes to just that one point. Then the preimage of f of x, so f of x is going to be the image of x, so that's going to just be that one point. So the preimage of that is everything. So the preimage of this function is not equal to x, it's equal to everything. So this one is not going to be true because we could have f of x is equal to just the single point 1, for example. Everything goes to 1, no matter what. And so that is a counterexample to the first one. Does that make sense?
Yeah, that would make sense.
If we were to then go through and do something for like another function, so let's say, all right. So if we had, here's our set A, X, Y. So X is going to go to some image here. So this is going to be f of x. And then maybe y goes to this set f of y. If we are looking at the stuff that is in both x and y, so that is, we are looking at this part. If it's in x and it's in y, that means that space has to stay inside this region here, because it has to be in f of x and it has to be in f of y. So this one is going to be true. Just looking at the diagram, we're able to see that part. Do you see how that makes sense?
Yeah, and then C would also be true, wouldn't it?
Yeah, C would also be true, because if we're looking at everything in here, that's going to be everything that's here. So that one is also going to be true. Then if we're wanting to do the same thing going the other direction, we would then look at the preimage of different sets. So we'd have, there's Z, there's W. The preimage of Z, that's going to be everything that maps to Z. So there is preimage of Z. And then we also could have, this is the preimage of W. So everything that maps to W. So if we look at what's in Z and W, the preimage of that, well, it has to be in the preimage of Z, and it has to be in the preimage of W. Now, the question is there equality? And it turns out that because f is a function, there is going to be equality. So, doing a little bit of work to figure out if there is equality, you would be able to show it. And then the preimage of B is a subset of A. That is going to be true. Because A can only map to B, so if you look at the preimage of everything in B, that's going to be an A. Okay. Did all of those make sense?
Yeah.
Alright, so those were all of the multiple choice and true-false ones. Did you want to go through any proofs in the last 15 minutes?
Yeah, we could do some proofs.
Alright. Let's see. Alright, so some of the free response ones, we have give an example of a function f going from the natural numbers to the natural numbers, which is injective but not surjective. So what would be an example that you can think of?
Would that be f of x equals 2x plus 1?
Yeah, f of x equals 2x plus 1 would work. Other ones would be like f of x equals 2x, f of x equals x squared. All of those would be examples of injective but not surjective functions. Let's see.
Is that all you would have to do for that one?
So you'd have to give an example. You might have to show why. So you might have to like prove it is injective, but show, and then also give an example of why it's not surjective. But that would be an example that would be doable to show it's injective, but not surjective.
Okay, yeah.
Let's see. Another example, or another problem. Let's see. Prove that f defined from the real numbers minus 2 to the real numbers minus 5, where f of x is equal to 5x plus 1 divided by x minus 2 is bijective. So if we want to prove that this is bijective, and let's see, and it says, and find the inverse. So if we want to show that this is going to be bijective, that means that we have to prove it's injective and that it's surjective. So which would you like to do first?
We can do injective first.
Okay. Okay, so injective. We start by assuming that f of a equals f of b. This then means that we have 5a plus 1 over a minus 2 is equal to 5b plus 1 over b minus 2. We could multiply both sides by a minus 2 and b minus 2. So that tells us that we got 5a plus 1 times b minus 2 is equal to 5b plus 1 times a minus 2. So let's see, multiplying everything out, let's see, we got 5ab plus b minus 2, which one am I forgetting? Minus 10a is equal to, on the other side, so all of that is equal to 5ab plus a minus 2, minus 10a, and minus, come on, draw, minus 10b. So now that we have this, we can then be able to cancel some terms. So 5ab is on both sides, minus 2 is on both sides, and then adding 10a and 10b to both sides gives us 11b equals 11a. So b is equal to a, which tells us that f is injective. Also, I apologize, but there's someone vacuuming right outside this room. So I'm sorry if that audio is coming through.
No worries, it's not that bad.
Okay. If we want to show it's surjective, alright, so to show it's surjective, we are going to say for any output y in our codomain, which is the real numbers minus 5, what we then need to do is we need to show that this is going to be, that there is some x involved that can get us to that thing. And so this is where we're going to actually be finding the inverse. So we are going to do this. Everything that I'm going to do in red is going to be our scratch work. This is not part of the proof. This is just our work to figure out what x do we need to pick. So we are going to say that y is equal to 5x plus 1 over x minus 2. And we are now going to try and solve for x. So that means that we get x, let's see. So if we want everything over x minus 2's, on the top we're probably going to want to try and rewrite 5x plus 1 so it's in terms of x minus 2's. So 5 times x minus 2, so we want to write 5x plus 1, that's equal to 5 times x minus 2 plus something, so that's 5x minus 10, so we would need to add 11. So we can rewrite 5x plus 1 as 5 times x minus 2 plus 11. And so then from here, that means that y is equal to 5 times x minus 2 over x minus 2 plus 11 over x minus 2. So that's just equal to 5 plus 11 over x minus 2. Subtracting 5 from both sides gives us y minus 5 is equal to 11 over x minus 2. Then we can multiply both sides by x minus 2 and divide by y minus 5. So we get x minus 2 is equal to 11 over y minus 5. So x is equal to 11 over y minus 5 plus 2. This is almost our inverse function. All you have to do is you say that your inverse is going to be this, where you replace the y's with x's. So it's going to be 2 plus 11 over x minus 5. So there's our inverse. And so you'll just state that at the end. There's your inverse. And now we're going to use that to show that it's surjective. So what we would do is we would say for any y in our codomain, so any y in the real numbers minus 5, let x be equal to 2 plus 11 over y minus 5. So we just state what we found in our scratch work, and then we would say, then f of x equals. And we're just going to plug in x and then just chug through until out pops a y. So f of x is equal to, let's see, it was, come on, scroll. Oh, scroll too far. All right, 5x plus 1 over x minus 2. All right, so that's going to be 5x plus 1 over x minus 2. That is equal to 5 times 2 plus 11 over y minus 5 plus 1 all over 2 plus 11 over y minus 5 minus 2. And now we're just going to be doing arithmetic and hoping that everything cancels out. So if we multiply the top and bottom by, well, let's just expand it out first. So that's equal to 10 plus 55 over y minus 5 plus 1 all over 2 minus 2, so that's just all over 11 over y minus 5. Multiply the top and bottom by y minus 5. So that's going to give us 11 times y minus 5 plus 55 all over 11. So that's going to give us y minus 5 plus 5 equals y. And that is showing that it's surjective. I hope you enjoyed this video and that it was helpful for you. Please check out some of my other videos, and please like and subscribe if you have not already so I can continue to make these sorts of videos. Have a great day and good luck with the rest of your math.